So thank you very much for the opportunity to speak here. I will talk about the theory of quantum gravity that I have proposed in 2017, which is based on the idea of fakeons, fake particles. And I will talk about its physical consequences leading to cosmology. So the idea of fake particle, which I call fakeon, allows us to make sense of higher derivative theories under certain assumptions. And it can be applied also to non-higher derivative theories. Basically, it is a novel quantization prescription, alternative to the Feynman I epsilon. This is to tell you that the entire talk comes from particle physics, scattering processes, scattering matrix, and although we will move to the classical limit and the corrections to the Einstein equations, we will see remnants of the origin of the entire formulation. So just to anticipate and to prepare you a little bit. And this idea leads to an essentially unique theory of quantum gravity. So the outline of the talk will be a brief introduction to the theory without giving too many details, because probably that's not in the spirit of this conference, and we will move quickly, or more or less quickly, to the physical implications, the classical limit, the remnants of the quantum field theoretical origin of this formulation in the classical field equations and their solutions, and in particular we will study the Friedman-Robinson-Walker solution and how to handle it and some properties of this theory. So what is a fakeon? A fakeon is an entity that simulates a physical particle in many respects. And for example, if it decays, if you look at its decay product, you would think there is a physical particle there. Actually, there are ways to distinguish them because the predictions are different. But the main point is that it does not belong to the physical spectrum of asymptotic states. So it is a fake particle in many other senses that I will explain to you. You can think vaguely, just to have a reference, of the Faddeev-Popov ghosts and the longitudinal and temporal modes of the gauge fields, which you introduce and later project away when you quantize a theory, a gauge theory. Well, in this case, when you introduce the fakeons and later project them away, they will leave a remnant, and the remnant will be one of the physical predictions that I will discuss, which is the violation of microcausality. The other important point is that this projection is consistent with unitarity, precisely like the projection of the Faddeev-Popov ghosts and the longitudinal and temporal components of the gauge fields. But the difference is that it does not follow from a gauge principle. So it is not protected by a gauge principle, but by a different idea. So the problem of quantum gravity is that it is either non-renormalizable or non-unitary in the usual formulations. So the problem is to make it renormalizable and unitary at the same time.
Sorry, what is it?
What?
It's, you said make it. What is it?
Quantum gravity.
Okay.
The problem of quantum gravity is to make it renormalizable and unitary at the same time. So if you want a renormalizable theory, you can insert higher derivatives, but higher derivatives produce this kind of propagators with polynomials of high degree in the denominator, and when you use partial fraction to decompose them, you necessarily have a relative minus sign. So at least one of them is a ghost, at least if you treat it as you would usually do. So you violate unitarity this way. Unitarity, let me remind you, is this kind of identity for the S matrix, and if you insert a complete states, a complete set of states, you have this kind of identity. Now you might think that if you have some unwanted degrees of freedom, you just throw them away. That's not possible. You can choose A and B, the in and out states, the way you like. What you cannot do is to throw them away from the completeness relation unless you have a symmetry principle, as in the case of gauge theories, or another construction that will have necessary to touch inside Feynman diagrams and what you have to compute inside, because otherwise what you throw away is regenerated back in the middle. So let's see what you should do. Let's consider a propagator, 1 divided by p squared minus m squared, with both signs in front, plus or minus. And normally the quantization is by means of the Feynman prescription, and the Feynman prescription contains an imaginary part, which is a delta function, which tells you that on shell you have a particle, if the sign is plus, or a ghost, if the sign is minus. Now what's a fakeon? A fakeon ideally would be a 0. Okay? Something that we want to have no propagation on shell. So what you do is, there's a few steps to do it. One is, well, first, just multiply and divide by p squared minus m squared.
Sorry, what is 0?
I would like to have a prescription that does not contain the delta function. So instead of being the delta function on shell, which is the imaginary part of this, multiplied by plus 1 or minus 1, let's say it's multiplied by 0.
But the delta function is from the I epsilon, isn't it?
Yes, exactly.
Okay, so you don't want to have I epsilon?
No. What I want to have is a different prescription, which is made of these 3 steps. Well, this one is not explained, but I will tell you in the next slide what it is about. So first you multiply and divide by p squared minus m squared, just to make things easier. And then you add a capital epsilon, a width like that. Notice that this propagator is 0 on shell. So this is going towards the right direction. But there is a point, however. Normally, if you take this big epsilon to 0, this is the principal value. Principal value is something you cannot use inside Feynman diagrams because of several. And indeed, that's not what you have to do. You have to define new kind of distributions that they are complex. You have to define the entire calculation from the Euclidean and then make a non-analytic Vic rotation that is not the usual one. But I will make the story short for this talk because it's otherwise I cannot talk about the application. So there is a certain procedure to following the loop diagrams. I just give you the result of that procedure, which is enough to allow you to compute everything basically, because the result is in the end very, very simple. So no matter what the procedure is, when you go beyond the tree level, let's say you want to compute bubble diagram, simplest diagram. Notice one thing, you have here some incoming particle, outgoing particle, and 2 virtual particles. If you cut it, you have 2 portions. One is a vertex, and the other one is the complex conjugate of a vertex, and you can build a modulus squared modulus. That's the imaginary part by means of the optical theorem. Basically, you can relate something that's contained in the loop diagram, which is the imaginary part or the discontinuity, to a physical process. Not always, but in this case you can. And basically, if you compute the bubble diagram as a function of the external momentum or energy, let's call it P0, and you complexify it, you find certain analyticity properties, which are very, very simple. In this case, you just have 2 branch points and 2 branch cuts. But they are on the real axis, where you want to compute things. Instead, in the imaginary axis, that's the Euclidean, you don't have any problem. Now, the Feynman prescription tells you to compute in the Euclidean and make an analytic Vic rotation. So that's just, you just calculate from above and here from below. Where the fakeon prescription tells you to compute the average, the arithmetic average of the 2 analytic continuations. That's the end of the complicated procedure that I will not go through here. But the result is very, very simple and allows you to make computations. This is a non-analytic operation because it is an average of 2 analytic continuations, but it is unambiguous. And the so-defined theory is unitary because so doing, you have no imaginary part, so you have no production of these intermediate particles. The would-be physical process is fake, and those intermediate particles are fakeons. Basically, any time you have a loop where 1 or 2 intermediate particles are the ones you want to quantize as fake, you do this instead of doing that. And that's it. So basically, this defines your theory. And in this paper, you can find proofs to all orders about the unitarity of the theory. Quantum gravity. We switch immediately to
So this is only defined at the level of Feynman diagrams,
or
I mean, if you want to do an operator with the calculators,
good point. That's the point of the talk. I will illustrate what happens, but let me not anticipate what will happen, keep the suspense a little bit. So, for gravity, consider this kind of action. You take the cosmological term, the Hilbert term with a redundant constant in front, which I insert just because I have a low energy limit and a high energy limit, and it's different. You need different normalizations in the low energy limit and in the high energy limit. So this zeta is positive. Then you have y squared up to a boundary term and r squared. And the constants must be positive here. Then you can add a standard model, covariantize if you want. Now, if you take this theory and you quantize it as usual by means of the I epsilon prescription, you get what is known as stellar theory, Stell theory maybe in English, and that has been known since the 70s. And the theory has a ghost. So what is the solution? And the solution is to quantize the would-be ghost as a fakeon. It's not explicit here, so in the next slide I will make it more explicit. What's nice about this action is that it is manifestly renormalizable. To make things explicit, however, you have to make a change of variables where renormalizability will not be manifest anymore, but the new prescription will be more evident. By the way, I can tell you that the fakeon prescription does not change the renormalizability properties because it is a change of a prescription, and the prescription is like a mass, and the ultraviolet mass is basically negligible. It's not as simple as that, but I have to make it as simple as that for the moment. So you have to introduce extra fields to disentangle the higher derivatives in order to have a non-higher derivative theory. And then you will have the Hilbert term. The Hilbert term is as usual. You will have a scalar field phi, which is the usual one you are accustomed to from the Starobinsky theory. And it has a very nice potential, a very nice action with a positive constant in front. Zeta is positive. And then you have a complicated action for the spin 2, a spin 2 massive field, which is chi mu nu. And then the coupling to matter is a little bit modified. So this is a little bit cryptic. Let me make it more explicit. If you make that action more explicit and you neglect the self-interactions, the vertices, and the non-minimal terms, you remain with a Pauli-Fierce action. That's what you expect. The point is, however, that the Pauli-Fierce action has a negative sign in front. And so you have necessarily to quantize this degree of freedom as a fakeon to have both renormalizability and unitarity. What about phi? Phi is a scalar field with the right sign in front. You can do both things. So even a physical field can be turned into a fake one if you use that prescription, because it works for both signs in front of the propagator. So there are two choices, and how to decide which is which in nature. I have no argument to prefer one or the other, so nature will, the hypothetical experiment will be able to decide what it is. So in the end, you have a theory that is described by a graviton triplet, and one field is massless, spin 2, that's the fluctuation of the metric, for example, around flat space. You call it the graviton. Then you have a massive scalar and a massive spin 2. The masses of those objects are related to the parameters that we saw in the action, and the new parameters with respect to Einstein gravity are just those two masses. So you have the theory you know of plus just two new parameters. And virtually you can make any computation in this theory as you would do for the standard model.
Sorry, you had 4 parameters in the beginning.
Yes, one is redundant, one is a cosmological constant, and 2 other masses. One is, if you want, a Newton constant, one a cosmological constant, and these two are the masses. So basically, you can do the computations at the level of Feynman diagrams as you would do in high-energy particle physics for the standard model. For example, you can compute the one-loop corrections to the graviton propagator, work out the resummation of the bubble diagram that gives the width of these particles. One interesting thing is that the unitarity implies that if a fake object has a negative sign in front of the propagator, its width is negative as well. So the width of the spin 2 is negative and the width of phi is positive. What's the meaning of a negative width? And S is the number of scalars in the standard model, Higgs field, and F is the number of Dirac fermions, and V is the number of gauge vectors. And this C, by the way, is known as central charge in conformal-field theory. The meaning of a negative width is that causality is violated. Micro-causality, actually. Now we can see it in detail. So, why? Take a bright Wigner, let's study it at rest, and you work out the Fourier transform of the bright Wigner for both signs of gamma. What's the result? The result is this one here. So apart from a sign here that doesn't matter, apart from some oscillating factor and the usual damping factor, you get a theta of gamma t. So if gamma is positive, you have a theta of t, and you have causality. And if gamma is negative, you have violation of causality. Why? Take, for example, a source. Use this as the green function, bright Wigner green function, to check the response. And due to this theta, if gamma is negative, the response is this kind of integral. The integral is from t to infinity. So you need to know the source in the future to predict the response in the future. So that's why you violate causality. Or you can reverse the thing. You can say that this is causing that. Change the effects with the cause. However, notice that this green function is either strongly oscillating, because these masses are supposed to be very large, or has a damping factor. So the violation is in the end short range. That's why you call it violation of micro-causality.
If gamma is negative, isn't it an anti-damping factor?
No, because you have theta of gamma t. So t prime minus t is negative as well, because you see, that's why you are integrating from t to infinity. What is the mass in nature? This is the mass of the fakeon. What could it be? It's a free parameter. We would need to measure it. This theory is perturbative as long as those two masses are smaller than the Planck mass. They could be much smaller than the Planck mass. Bounds we can put from observations are very weak for the moment, at least the one I checked. Let's say they are 10 to the 12 GeV, very smaller, much smaller than the Planck mass. Well, 10 to the 12 GeV means that this oscillating factor is a very rapidly oscillating, so it averages most of effects away, and that corresponds to a time interval of 10 to the minus 36 seconds. That tells you that around everything is fluctuating with this kind of frequency, and there is no causality and no notion of time, past, future, and present, or event below 10 to the minus 36 seconds. Well, we cannot measure those kind of intervals, and checked from the web the shortest amount of time that we can measure. Maybe you know better than me about these things, but the shortest amount of time that you can measure directly, I found, comes from laser pulses, and it is 10 to the minus 17 seconds. That's 20 orders of magnitude smaller, bigger than this.
So then, doesn't it depend on the frame? So if you boost the system,
Okay, good.
you boost the effect.
That's a recurring question, and I will put a paper in the couple of weeks or something, maybe more, on the archive on that. The answer is no, because anytime you change your Lorentz frame, you introduce further errors, and you worsen your measurement. You have to understand that you cannot just take and speed yourself up to velocities close to the velocity of light. So if you take all macroscopic objects of the universe, the relative velocities are around 1,000 kilometers per second at most. And that doesn't change much here. But in principle, yes, if you could go to a very, very fast traveling relative inertial frame, you would see the effect, because the effect is there, which would be the same as going to 10 to the minus 36 seconds or below that.
But this is a Lorentz invariant theory, so
yeah.
Why should frame matter, or that's not understand?
The frame matters because when I say, for example, that we have this kind of accuracy, we can measure time more precisely at 10 to the minus 17 centimeters, that's in our frame. And one could say, okay, but if you change the frame, you can see things differently. Unfortunately, we cannot change the frame at will. At least practically, in principle, we could.
But I guess the other question is, if you need to know the future to know what's happening now, then is this a predictive theory, or?
Yes, we'll see. So let's move towards more concrete problems. I will complete this part telling you some details from quantum field theory about what the projection is, because now we will apply it in the classical limit. So basically, you don't have the fake particles as asymptotic states. You just don't put the sources for them. They are zero. But what is a source? The source is the derivative of the one particle reducible variation function generated functional. And so it is the fakeon field equation. That means that you solve it and you insert the solution back, and that is what you get. How to solve it, however, with the fakeon prescription that I told you before, which inside diagrams is kind of tricky, but at the tree level is quite simple. So let's do this at the tree level to study the classical limit. So what is the point here? I started from a classical action that I told you about. That's not a classical action. Why? Because it contains something that has to be thrown away. It's like having a gauge-fixed action with Padeva ghosts, longitudinal modes of the gauge fields. You don't trust it as a classical action. You have to throw something away. Here you do throw those things away by following this procedure, and that is what you get, what gives you the classical limit. So you take this action, work out the field equations, and if this is a fake, you have to solve the field equations with that prescription. Now we will see in a moment what it means, and insert the solution back in the other two. If both are fake, you have to do the same for both. Well, this is easy to say, but it's not easy to implement, because the fakeon prescription and everything I've told you comes from particle physics, and you know that particle physics is defined perturbatively. So everything I'm going to say now is also perturbative, and the problem will be how to resum the perturbative expansion and what to get from there. But in the classical limit, things simplify, and you can take the formula I wrote before without caring too much about analytic or non-analytic continuations. That's a principal value. Fine. So you solve the fakeon equations with this, and you insert the solution back, and that is the projected action, the classical action.
So this now contains stuff coming from the future and the past, right?
This average contains this kind of stuff. Let's see it in a very simple example. This is a non-relativistic mechanics. So if you ignore this part, it's just mv squared divided by 2 plus an external force. I add some higher derivative term. And the equation of motion is like this. The external force, and then you have a kinetic operator here which factorizes. What you do is as follows. Take this kinetic operator, throw it to the right-hand side by inverting it with this fakeon prescription. And what you get is a modification of F equals ma, which is ma equals certain average of it. And the average is computed with this oscillating factor, and the oscillation is very, very rapid. Suppose that this tau, which is free here, but in nature could be 10 to the minus 36 seconds. So basically, if you take the limit tau going to 0, this goes to a delta of u, and you get just f equal ma. But you have a tiny, tiny departure from that. Now the point is that this carries remnants of quantum field theory because it's defined from quantum field theory. So everything is perturbative, and what to do normally when you make this projection here in gravity, you don't have just that. This is the expansion around flat space. The metric will go inside the Green function. And let's see what happens in the case of the Friedmann-Robertson-Walker metric. But before that, we anticipate a little bit the problem, again, with this kind of toy model, where the same as before, the only difference is that instead of putting an external force, I put a self-interaction, because normally that's what we would do. We have to solve things self-consistently. The equation is the same, but in the right-hand side, you have the interaction. So you have to remove this operator, throw it to the right-hand side with this average, and again, this is the projected equation of motion. Is it? Well, actually, it's again a formal thing, perturbative, because you have to unfold it, if you want. Now, I do not tell you the details about the procedure, but I tell you what happens. If you make the projection and basically want to rewrite this Lagrangian or the equation without the higher derivatives, because if it is projected, somehow you lost the extra degrees of freedom, what you get is an infinite series, the equation of the Lagrangian. An infinite series, this is v squared divided by 2, then there is the self-interaction, and then you only have position and velocity, and the infinite series is an asymptotic series. So this vindicates against your attempt to find a closed form of the equations. We are talking about the equations, not even the solutions here. You cannot even write the equations in a closed form as you would normally, as it would normally happen in quantum field theory. But now it happens at the classical level. And if you check the coefficients, they grow extremely rapidly, yet this is an asymptotic series, and most of the time an asymptotic expansion is very useful. Why? Well, if you, for example, you might know how they work. If you take a coupling equal to 1 over 10, let's say, and you check the first order is very rough.
So all you're doing is you ignore lambda, solve it, and then put it back in, and you just do it or solve it order by order, or is that?
You have to, yes, you have to write x as x0 plus an expansion of x, right. And then you put it inside, and you use the machinery. So with some asymptotic series, what happens is as follows. Let's say the lambda is 1 over 10. So the first order gives a very rough approximation. Second order gives a more precise one. And then you have a continuous line here, check. That's the third, fourth, fifth, sixth, seventh, eighth, and ninth order. They all superpose. Very precise. Basically, they get you to the right solution. Then you can say, okay, as I go to the 10th order, 11th order, you would get something totally crazy. You cannot even write it down. This is what happens with asymptotic series. They do not converge, but the first few orders already pick the right solution. How many orders? And then they become crazy. The formula is this one. Basically, you take the coupling, take the reciprocal, the integral part, and you will get 10. So to be safe, let's say 9. Now, what happens if lambda is equal to 1? If lambda is equal to 1, you don't have any help from the expansion because you have to stay to the 0th order. And unfortunately, now we will see that this is the case for the first fractions of a second of the universe because you don't have the expansion parameter. So let's move to the final part, which is the Friedmann, Robertson-Walker metric, and see what happens there. So this is the metric with the usual parameterization with kappa k generic here. Here, the triplet becomes a doublet because the chi mu nu is coupled to the y-squared term, and the y-squared term it doesn't contribute because this ansatz is Weil invariant. So you basically get the Starobinsky action. Therefore, I am assuming now that phi would be quantized as a fakeon, because if phi is physical, you just have what you would normally do. Again, there is no real reason to quantize as a fakeon. You just need to quantize that as a fakeon. But so this is one possibility. Now you can write down the unprojected equations. This is something I didn't notice in the literature, so it might be useful for you even if you do not apply to fakeons or anything like that. If you write the equations in this combination, which is the one good for radiation and vacuum energy, the left-hand sides factorize. They factorize the Einstein-Friedman, let's say, terms times two differential operators, which are written here. Okay, with depends on the Hubble constant and the factorization is useful because it's exactly as we had before. When you have a kinetic operator higher derivative, because this is higher derivative, but factorize the projection is, so to speak, easy, at least. But you see that these operators now depend on the matrix, so we are not in flat space. We have already resummed some corrections to orders. And so you define the projection as before. You have the principal value, which is also the average of the retarded and advanced potentials. And in the end, you get these kinds of equations where you move those operators to the right-hand sides, and there you have those averages. Or if you want, you can turn things around and get exactly the Friedman equations, but with modified pressure and energy density. Okay, this is formal again because it's perturbative and the average depends on A. Everything has to be self-consistently solved. Rho depends on A. And what to do? So most of the times you will get into asymptotic series. And if it is far away from the Big Bang, maybe that's helpful. If it is close to the Big Bang, then you have the problem that you don't have an expansion parameter.
Sorry, do rho twinkle and P twinkle now satisfy the conservation equation?
Yes, they do. It's an implication of those. But as in quantum field theory, you don't lose hope because there are things that you can resum to all orders. Very remarkable things, of course. One example is anomalies. They are one loop exact, and the corrections are 0 plus 0 plus 0. So, and that is very powerful because through the Toft anomaly matching conditions, for example, you have relations between the ultraviolet and infrared behavior, or you have the renormalization group flow. That's also an anomaly, the anomaly of scale invariance. Or you have the width, we have already seen it, and that is the summation of a bubble diagram. So there must be situations here where you can handle the resummation exactly by miracle, and this is the case. It's radiation and vacuum energy, and also the combination of the two. Don't know if this is useful in any situation, but you can write down this state equation, which combines radiation and vacuum energy. And then the solution, the exact solution looks like this. That's easy. Why can you solve it exactly? Because for that combination, either this or this are 0. Okay. And if one of the two are 0, the average of 0 is 0. That's one thing for sure that you know. That's why you can solve it. So one of the equation is solved because the average of 0 is 0, and the other equation can be the continuity equation instead of this one, so solved as well. And the solution looks like this. It depends on two constants here, and rho depends on the third constant, and the only departure from Friedman, or Einstein if you want, is that the relation between the three constants contains this effect, this correction, which depends. The only place where the mass of phi enters, and otherwise you would get this. So there is a small correction, but only in this case. But in general, you have to define the projection perturbatively, and then you enter into a dark area of the theory. For example, dust, P equals 0, you would think it's the simplest case. No, it's the most complicated case here, and any other case is leads into that. So to conclude, let me make a comment on the violation of microcausality. The relation between higher derivatives and the violation of microcausality has been known for a long time. You can find, for example, a good, nice discussion in Jackson's books on classical electrodynamics, where you can take the Abraham-Lorentz force that describes the back reaction of due to the radiation emission due to the acceleration of a charged particle, and the runaway solution can be eliminated. It's like eliminating the ghost in favor of a violation of microcausality. This is done as follows. This is the equation. You factorize a kinetic term, which is like that, in that case. You throw it to the right-hand side. What is the prescription there? There is no fakeon prescription there, but the idea, I don't know who did it historically, because Jackson doesn't say. Somebody told me it was probably Dirac. Anyway, the idea is very simple. Just require that tau being 0 is the correct limit. Then you have just one solution. You eliminate the degree of freedom, you just have one solution, but the integral is from t to infinity. It's the future. But there is a damping factor, and so you just need a little bit of future. 10 to the minus 23 seconds here, still below what we can measure. You might have heard of the Liebig models, which are particular higher derivative theories. They also claim that they could make sense of higher derivative theories, and actually my entire investigation started from that. My initial purpose was actually to disprove their idea, because I could not believe it was possible to make it work. But in the end, I found that their formulation was just incomplete. The third point of the prescription was missing, and this average continuation, but it could be made to work. So you can understand those theories better using fakeons. But the point is they immediately realized that there was a relation between what they were doing and a violation of microcausality. Then you might have heard of the Feynman-Wheeler electrodynamics, which would contain the analog of a classical massless fakeon, because they have a propagator like this, principal value of 1 over p squared. The sum are advanced and retarded potentials. And however, in that case, they need to eliminate it because it is massless, and a fakeon cannot be massless, because the scale of the violation of microcausality is the mass, 1 over the mass. So if the mass is 0, you violate causality and not just microcausality. And so they came up with a complicated theory, which is called emitter-absorber theory, and in the end, they recover causality because they show that due to this complicated interpretation, this green function gives the same physical results as the retarded potentials do. Then you can move to quantum field theory. Quantum field theory, you don't find too many textbooks that contain the complete dual-order discussion of causality, so I refer to Thorsten-Weltmann diagrammer, where you can find everything diagrammatically. But the point is that in quantum field theory, it's hard to define causality as a condition for the S matrix that's on shell. You have Bogoliubov's condition, which is for correlation functions of shell. You have the Lehmann-Simansky-Zimmermann condition, which is that fields should commute outside the light cone. Yet it is it's hard to accept it as a definition with a general consensus, which might work for macrocausality, but in the case of microcausality, still things are up in the air. So my personal position is as follows, that it is hard to elevate microcausality as a fundamental physical principle, so just do not consider it, which is good for my proposal because it would violate it. Macrocausality is fine. So this theory violated. It's not right to say it violates it because I would have to know what it violates to say that it does violate. Let's say it doesn't not allow it, as far as I can understand.
So basically quantum gravity, you mean like your version of quantum gravity?
Microcausality is probably a blunder. So due to our limited insights and what we learn from our environment, which shows some causality, and we extend it to arbitrarily small distances, but that is, I think, a stretch. So when I talk about causality or microcausality of the violation, I just downgrade this concept to a very vague idea that reminds of the fact that the equations have an unusual form. They are non-local, they involve the future of the external force, but then a sort of fuzziness of the input-output relation. Okay, let me just conclude with a comment on the other approaches to quantum gravity, because referees asked me to do that, and they were complaining that I do not compare my approach to the others. I didn't want to do it, because if I had to do it, I had to criticize them, and I didn't want to let them reject the papers for that. So I started inserting comments. Of course, the criticism is very easy here. With my theory, you can compute. With those, you cannot. Well, I discovered that the referee was happy, and some other referees were even enthusiastic of these insertions. Thank you very much.
String theory has more enemies than friends. Is that what you're saying?
Thank you very much.
Questions?
So, did you look at what happens if you do a sort of Hamiltonian analysis? Because typically when you have variable derivatives, these ghosts are Ostroglavsky ghosts, which tells you that your Hamiltonian is unbounded, etc. So how does your procedure, can you see your procedure curing the ghost in the Hamiltonian sort of?
In the case of a Hamiltonian quantization, the projection means that you have only creation operators for the physical particles. You do not have creation operators for the unphysical particles. So your Hamiltonian, at least since this is perturbative in the free field limit, is certainly bounded from below, and then you have the perturbative corrections. Just because the space of states is reduced, and the Hamiltonian is unbounded in the full space where you have also the creation operation for the fake particles.
Yes.
In general, when you do the expansion to calculate the function, that is the classical action, of course you have non-perturbative effects because this expansion breaks down, as you're saying. And one would expect that, of course, the non-perturbative effects have extra coefficients. And if I can tell also from what you were doing in the simple solutions, these new non-perturbative coefficients should correspond to the extra initial conditions you need in your original system, which should come up from non-perturbative corrections. So the statement eventually, the whole theory is non-perturbative stable must be subtle.
Yes, correct. So as far as I know now, if unless you really understand non-perturbative quantum gravity, so you understand the non-perturbative version of this projection, and unless you are able, as in the simplest examples that I gave you, like the radiation of vacuum energy, to find by some miracle the exact solution, you might run into regenerating what you were trying to get. And the solution, the final solution, is in non-perturbative quantum gravity. So, but that hopefully is only relevant when you don't have an expansion parameter, but that would lead to the conclusion that maybe the first moments of the universe, until you will solve non-perturbative quantum gravity, are unknowable.
Just to remark is that causality in the ordinary standard quantum field theory can be enforced, as you probably know, through Schwinger-Keldysh, a closed time path formulation. And then that is a definition of microcausality. Despite, I don't know.
There are definitions. I don't dispute that. That's
have you looked at? I guess the question is: have you looked at what happens in your formulation for Schwinger-Keldysh?
No, it's one of the things that I have in program, but I've not cannot answer right now.
Yes.
So this theory is renormalizable to how many groups?
It's renormalizable.
To
All others, yes.
Yeah, quadratic gravity is renormalizable. I guess that's the best color for it. Just not unitary. But I guess so. This is. I'm a little bit confused that your statements seem to be very strong. You're saying you have a very predictive calculable theory, but I mean, what have you predicted? So,
Well, for example, the point is that you have to find the hard part is to find something that you can measure today, right?
Yeah.
And so I can predict a lot of things, like for example this width, which is an amount of time that basically measures how long the duration of the violation of microcausality. But this is high energy physics.
But I mean, that's not a prediction. You're saying that that's that. I mean, what is the prediction exactly? What is that kind of observable you're talking about? It's not. That's not even clear to me.